talked about on Monday, this idea that if you heat up a liquid that's like it has a bell jar over it, and it's in dynamic equilibrium with the air that's in the bell jar. If you heat it up, you know that those gas particles are going to go faster. So that increases your pressure. The other thing is with the more thermal energy, you're going to have more liquid going into gas phase. So you kind of have two things that creates a new equilibrium vapor pressure at that higher temperature. So I've got like several different ways to look at that. All this is at these temperatures, and this is in the Celsius scale. So what is 0 Celsius in the Fahrenheit scale? 32. So this would be freezing. 32, getting warmer and warmer. And then the equilibrium vapor pressure of water is pretty low. These units actually are torr. And remember, a torr is exactly equal to a 1 millimeter of Hg, 1 mmHg per millimeter. So notice as we increase the temperature, you increase the equilibrium vapor pressure. Increase temperature, increase equilibrium vapor pressure. Now, instead of actually seeing it in a table like this, a lot of times it goes well in what we call an equilibrium vapor pressure curve, which I think is coming up. Just another set. Okay. Columns of equilibrium vapor pressure, again in units of torr, temperature, pressure, temperature, pressure, temperature, pressure. So I know they're kind of small, but actually the problem that we're going to have to come back in. I can't remember if it's 25, maybe it's 25. So if you find 25 on here, that equilibrium vapor pressure is 23.8 torrs. Okay, that's how that would work. Okay, so all this is saying is in our experiment, then we just need to know the temperature of our system, and then we'll know what the pressure of water is. So here we go. We're going to work a problem. Let's see if my pen works. So what is the physical phase of the potassium chlorate? Thank you. Solid. What's the physical phase of the potassium chloride? It's also solid. Solid, solid, gas. Now, the problem with this experiment, if you read it a few times, is it has this sort of setup where, I think I'll do it down here. Here we have our, we have a bottle, must be sealed of sorts. And this is our solid KClO3. We're going to heat it up and we're going to stop it, but we're going to have a tube that can actually, pretend that's a tube, not a line, can actually come over and go into this inverted, we could make an Erlenmeyer flask if we wanted to, okay? I did a problem the other day, and that's a pretty ugly looking situation, but hopefully you kind of get the idea. That looks like a tooth. But the point is that's our heated up KClO3, and then collected in here. I'll go ahead and kind of show you that some gas has been collected, and we'll go ahead and make the water level here. The gas up here, that is our O2. That is that. But inherent to this design, like I said, I'll put a G here for gas. Also in that same region, we also have H2O gas. Okay. So everything that's said about the product here in a minute actually is going to apply to both of those. Now just to remember, just to remind you how this works, and I kind of tease Dalton's law of partial pressures, is according to Dalton, our total pressure actually, and it makes sense, is additive, a combination of our oxygen plus our water vapor. This information right here is in regards to our total. So let's read this. It says if 0.250 liters of gas is collected, so down here, right there, the volume for that volume total is 0.250 liters. And the temperature that the gas is collected is 25 degrees Celsius. You guys are probably getting pretty good at adding 273 or 273.15 to that to get the units of Kelvin. And it gives us a total gas pressure, so I'll go ahead and call that P sub T is 764 millimeters of mercury. Okay, so that is all about a story or information about our combined oxygen and water. Now the questions, and I think I've written where the questions are going to go. Hopefully you can see that black behind that. We have two questions. What is the mass of only the O2 molecules? What is the mass that O2 molecules collected here? Okay. And what is the mass then of the potassium chloride that must have been heated up? Well, here we go. If we look up here, do you see what's missing? In this information up here, our total, total number of moles. But that's not how I'm going to do it. How am I going to do it? I know. What I'm going to do is take this total pressure, and I'm going to rewrite this. The total pressure, and I'm going to recognize that that's pressure exerted by my oxygen, which I created, plus the pressure exerted by my water vapor. Here's the deal. All we got to do is look on the table for this at 25 degrees Celsius. And I was right. It is 25 degrees Celsius. So we're going to get that from the table. That P sub T, that's our 764 millimeters mercury. So right off the bat, then, I can get the partial pressure of oxygen. If I can get the partial pressure of oxygen, I know the volume of the oxygen, the temperature of the oxygen, and I know the partial pressure, so I can get to the moles of oxygen. Does that make sense? That's what we're going to do. Once we have the moles of oxygen, we're going to backtrack, use stoichiometry. So we have those moles, we're going to go ahead and get these moles and get to the mass. That's it. So again, in this sort of problem, what we have collected in that inverted bottle over there is both oxygen and water vapor. From the table, we can look up. And actually, I'm pretty sure that the title of the columns in the table are units of torr, but I've kind of, if it's okay with you, just skip from torr to millimeters of mercury because they're exactly equal. So from the table, at that temperature, 25 degrees Celsius, our partial pressure of water, the equilibrium vapor pressure of water, is 23.8 millimeters of mercury. Cool. Now I can rearrange this. I can rearrange this up here and say that my oxygen will be equal to my total pressure, which I had in the problem, minus the partial pressure of my water vapor, which is 23.8 millimeters of mercury. I'm bad about sometimes working problems and not seeing them obviously, but do you guys see where to do these subtractions and such, we don't have to convert from millimeters of mercury Hg to atmospheres. If we use the ideal gas law equation, then we need to, which we will here in a minute. So do that subtraction, round it to the nearest unit of 1, because I only have the nearest 1 here, the tenths here, so I got both ones. You're looking at 740 millimeters of mercury, where the decimal is important here to show that the uncertainty begins at the 1. So now for PV is equal to nRT for the oxygen, we know the volume, we know the temperature, we know the pressure, and now we can get to N. So if I rearrange PV is equal to nRT, solving for N, of course that's PV over RT. Again, I really urge you to start out with PV is equal to nRT and then kind of rearrange and solve for what you need. So we are going to have to go ahead and get from millimeters of mercury into units of atmospheres. We also need to fix our temperature. So 25 Celsius plus 273 is 298 Kelvin. And here's fixing our pressure, partial pressure of oxygen. We left it in millimeters of mercury. It was 740 with 3 sig figs millimeters of mercury. Of course, 1 atmosphere over 760 millimeters of mercury will do the conversion that we need. Down to 3 significant figures. You get the partial pressure, the pressure of oxygen is 0.974 atmospheres. So now we're ready to go ahead and to plug into this equation. So the number of moles of oxygen must be the pressure, 0.974 atmospheres. Also the numerator, we have that volume of 0.250 liters that was given in the original problem. In the denominator, we have the ideal gas law constant, 0.082058. Units then would be liters, atmospheres per mole Kelvin. And then also in the denominator, we have the temperature, 298 Kelvin. And again, when I work these, I usually put 298 Kelvin, in this case like over 1, so then my units of Kelvin cancel. Units of liters cancel, units of atmospheres cancel, we're left with 1 over mole in the denominator, which is moles. So we round to 3 sig figs, and I get 0.00998. The units, of course, would be moles of O2. We've done a lot of this. Of course, now to go from moles to, if you read the problem, I want grams, I can use the molar mass of O2. And it's funny how recently I haven't been showing my molar mass calculations, but here to get the molar mass of O2, we take 2 times the decimal number for oxygen, which is 32.00 grams per mole. So if we use as our first term the moles, 0.0095 moles of O2 over 1 usually. We're going to use the non-flipped version of the molar mass, 32.00 grams over 1 mole. Round to 3 sig figs, and that will give us our grams of O2, 0.319 grams of O2. So there were 2 questions. What's the mass of O2 that's collected over there in your gas, which now we got. The other question is, what is the mass of the KClO3 that was decomposed to get that? So to answer that second question, we're going to piggyback on that. If we start with 0.00995 moles of O2 over 1, molar mass of potassium chlorate, KClO3, 1 times 39.10 plus 1 times 35.45 for the chlorine, for the oxygen, plus 3 times 16.00. It's a heavy sulfur gun for 122.55 grams per mole. Now we're ready to knock out the mass of KClO3. So our first term is going to be that 0.00995 moles of O2 over 1. And then I'm going to use the stoichiometric ratio, which it's not here, okay, but if you go back to the balanced equation, you're going to see the coefficient in front of the O2 is 3, has a coefficient of 3. The coefficient in front of the KClO3 is 2. So here's where we have 2 moles of KClO3 over 3 moles of O2. Our moles of O2 cancel. We're ready to finish it up. Now that we have moles of KClO3 to go to grams of KClO3. So we're going to use that molar mass, 122.55. We're going to use the non-flipped version, 122.55 grams of KClO3 over 1 mole of KClO3. Unit-wise, moles of O2 canceled before, and now moles of KClO3 cancel. We have units of grams of KClO3, which is perfect. But we're only allowed 3 sig figs in our answer. So I get 0.813 grams of KClO3, potassium chlorate. All right. So there you go. I think I might have told you that I did 4 problems, and then I had the other 2. Actually, of those last 2 problems that I just did the other day, only one of them is over water. The other one's just kind of preliminary water. So take a look at those. Those will be due. You guys' test is Friday, this room, at noon. So those will, seems like everything should be due when you come to take your test. And remember, that would be if you had any problems that any assignments that you didn't get done, you return those too. But between now and Friday, we have a Thursday. which Thursday, tomorrow I'm thinking of it. I think I gave this to you before. So we are going to do experiment 15. Experiment 15. Some years I do actually, that's kind of a short one, so I do that one and another one. Some years I do the other ones a little shorter. But my husband and I were talking about, well, which one are you going to do? Which one are you going to do? And this was the one that I gave you originally. This one should help you on the test. So you're going to earn lab credit by, you know, collaboratively or whatever. Before you leave, knock out the calculations. Okay. All right. So the last topic we have is dun dun dun. Oh man. What's short? It is short.
So when like converting from Celsius to Kelvin, it doesn't matter if we use 273.15 or 273.
It depends. You don't want the 273 or 273.15 to add to introduce the uncertainty. So if you had, well,
I think I understand what you said.
Yeah, because if you were converting a temperature of 25.4, then you wouldn't want to just add 273 because then that would make you limited to the nearest one. Yep. So yeah, sounds like you got it. So it kind of depends. You can't go wrong with doing full-blown 273.15, but sometimes you don't need to. I know we're all about saving a few strokes. So, all right. Gases behaving badly. I just think that is so fun. So we came up with the ideal gas law equation, PV equals nRT, and that assumes that gases are behaving ideally. And we already talked about what ideal gas behavior is, and we're going to see it here again. But just in general, if it's behaving ideally, we said that, what did we say? The size of the particle is negligible. Basically, it has no size, no volume, which is weird. And then we said that every individual gas particle is independent. They don't care about the other ones. So we need to talk a little bit about what happens if gases are behaving badly. Gases are not following PV is equal to nRT. It's called non-ideal gas behavior. And I'm going to build up to something called the van der Waals equation, which just basically takes PV is equal to nRT, and it kind of adds on to it for non-ideal behavior. So in general, the closer something is, the closer the gas is to the liquid. Okay, so here, do you remember we had, it's my solid, it's my liquid, and then here's my gas. Oops, I should put these over here. So for gas particles, of course, they're way far apart. They have a lot of kinetic energy. Liquids are closer together. They have less kinetic energy. And solids are really close together, okay, and they don't have as much kinetic energy. Kinetic molecular theory. So this says that the closer the gas is to being a liquid, okay, if it's like this, if your gas is like this, it's going to be non-ideal. Non-ideal behavior. Okay. So this actually, if you figure, most people are good with this. To get a solid to a liquid, I add heat, right? To get a liquid to a gas, I add heat. So does this make sense that if you are looking for something to behave non-ideally, then it's going to be cold? Okay, and the other thing, I don't know if you can tell it by this picture, but that it's going to be high density. That just means they're close together. And to me, which came first, the chicken or the egg? Are they close together because they have more intermolecular bonding we've talked about, or because they're close together, do they have more intermolecular bonding? So anyway, so if we contrast that to a gas will behave ideally, the closer it is to being a gas, of course, you're talking about hot, okay, or warm temperatures, and this is what I'm going to call low density. So that's about it. Before I move on, one of the things I put high density, low density here. Does this work for you instead of density? Or over here, low density, I'm going to go ahead and put low pressure. Low P for pressure. And over here, high density, I'm going to put high P for high pressure. So the further the gas is from being a liquid phase, okay, so if it's over here in its gaseous state, the more ideally it will behave. In next semester, in General Chemistry 2, we'll do a lot with these. This is called a pressure, temperature, phase diagram. Pressure, temperature, phase diagram. And hopefully, these look like similar colors, but actually they divide they divide the 3 physical phases. So from left to right, at the lower temperatures, you would expect this to be a solid, okay? That sector is all, this case is water, is in its solid state. This right here, this is water in its liquid state. And this right here is water in its gaseous state. Solid, liquid, gas. They kind of look like a Y. And all phase diagrams kind of have this similar look to them. And this is kind of fun. So here actually, where these regions intersect in a graph should be regions where those 3 physical phases intersect, and they do. Actually, that's going to be our critical pressure and critical temperature. It's pretty cool. But anyway, the reason we're talking about it here is that the more, just a minute ago, we said the higher the temperature, so along the x-axis, that would be over here to the right, okay? And the lower the pressure, so this would be down here, this is lower pressure. So in this region, gases behave ideally, okay? And then in this region, if you increase the pressure and or cool it down, you're going to be into liquid territory. Now, you might, and we're not going to talk about it today, we'll talk about it more in Gen Chem 2, but isn't this fun? What about here? What about this? What if you have water vapor in this pressure and you cool it down? It's going to go straight from being a gas to being a solid. Of course, that we call that a type of sublimation or deposition more specifically. Here it can go from a solid to being vapor without going through its liquid phase. That's called sublimation. But my point here is you figure you're going to get ideal behavior here at high temperatures and low pressures, okay? And you're going to get non-ideal behavior or less ideal behavior if it's in this sector right here, a gas anyway, as you increase the pressure and you reduce the temperature. All right, so ideal gas behavior. This is actually what we talked about when we started talking about gases in general. It's behaving ideally if basically each gas particle is in it for itself. There's no interaction with other gas particles, which to me, that is a pretty good bet if you have a lot of space between gas particles. And in that case, you're representing something that's in a low pressure. So this is great at low pressures. It's also great at high temperatures. So you figure at low pressures they have a lot of room, but at high temperatures, are they going fast or slow?
Fast.
Fast. At high temperatures they're going fast. So they're less likely to run into each other. This other part of it is the size of the gas particle is negligible. I guess this is where it's emphasized, the whole being on their own. The size of the particle is not much, the volume is what we're talking about, relative to the container it's in. And the larger the container is per gas particles, the lower the density, lower the pressure. Actually, that is favored at low pressures. So the thing in italics then is basically what we said. The gas will behave ideally if it's at high temperatures and low pressures. So wait, sorry, high temperatures and low pressures. Just trying to think of the phase diagram. So finally we build up to that equation I told you about called van der Waals equation. And I did this on purpose, so you see the PV is equal to nRT. So that's kind of embedded in van der Waals equation to describe non-ideal behavior of gases. But what's added are these terms. So notice for the P, we have something added to the P, and it is the quantity A times N over V, that's moles over volume, raised to the second power. To the V term, we need to subtract B times the number of moles. Now, these A and B's, actually, those are called van der Waals constants. So I'd have to give those to you, or somebody would have to give those to you. The homework for this last part actually has you do one problem where you work it out, assuming ideal behavior, and then you use van der Waals constants, A and B, and you work it out again to see as if it was not behaving ideally. All right. So this term here, the A quantity N over V raised to the second power, that's called the pressure correction term. Okay. And then the Bn, again, A and B are constants. You have to look them up for a specific gas. The Bn is called the volume correction term. So PV is equal to nRT, which is put something up, add something to the P, we subtract something from the V. So this right here are for, I don't know, there are eight different gases, a value for A and a value for B. Now, before we leave, I thought I would take one more look at the title of this talks about dimensional consistency. Remember how that works. So let's pick on, right quick, let's pick on the A. So units of A are going to be atmospheres in the numerator, liters squared in the numerator. In the denominator, we're going to have moles squared. That's my units of A. I'm going to go ahead, and for N, that's going to be moles. And for V, of course, that's going to be liters. And I'm going to square that. You can find your way around a lot of physical science problems if you just look at the units. So do you see where my moles squared will cancel and my liters squared will cancel, and I'll be left with units of atmospheres? So basically, I'm taking units of atmospheres and adding units of atmospheres. Just for kicks, let's double check that B term over there. So for the B, the units are liters, moles, and then of course N is moles, and then moles cancel, we have units of liters. So here I'm taking liters minus liters for that term. All right. These last two problems, I checked them before I came. One of them is really straightforward. Like 101 says, under which of these conditions do gases behave most ideally or least ideally? Okay, then they give you some pressure and volume possibilities. So that's 101, and then 104, that's also due for this part, is the one where I said they were dealing with carbon dioxide. They give you volume, moles, and temperature, and they ask you to knock out pressure using PV equals nRT, then knock out pressure using van der Waals equation, and kind of compare the two. Let's go ahead and make those. They'd be due, again, when you come take your test Friday, but those, I'll make them worth 0 points. So if you do those, then I'll put the number in there. It's another way of giving you extra credit. Okay? So there's just those two questions. All right? So that's all I got. See you tomorrow in lab. We will be dealing with the Bunsen burners again one last time.
Go ahead and take that snake out of class.
Oh, I do. I would love some homework. Thank you.